So, Chapter 5, Forces and Motion, Lesson 1. We have to understand some of these terminologies, right? Inertia, right? Mass, force, and acceleration. And these are some really important definitions, okay? And physics is study of how things happen, right? Not always why. I think we talked about that earlier, okay? How things happen pretty much explains the, how of things, but why, we really don't know, okay? So some important definitions that we need to understand, okay? Mass and inertia, okay? Inertia is a concept. It refers to the amount of resistance an object has to change its current state of motion or rest. So it doesn't always have to be in state of motion. It could also be or at rest. Okay? And since it is a resistance of current state, whether it's in motion or whether it's at rest, more massive it is, more inertia it possesses. Okay? So it's very important to understand that mass and inertia are pretty much equivalent. Mass, right? Mass. Besides 1 hour of torture for Mr. Kim every Sunday, right? Mass in physics quantifies inertia, right, with standard kilograms, and allows us to compare two different objects. So it pretty much defines amount of matter that object possesses is what mass is. And greater the mass, greater the inertia. Okay? So if you could think of an elephant on a skateboard and a tiny mouse on a skateboard, which one will be easier to push? Why? Yeah, right? Which one would be easier to stop if it's coming at you at 30 miles per hour? Right? Right? Because it has less mass, which means it has less inertia. Okay? Elephant would have such a huge inertia. It's in motion, and it's going to want to stay in motion. All right? Mouse, you could probably just stop it with your foot, right? So mass and inertia are two same things. Here's another example. An 8 kilogram mass has twice the inertia as the 4 kilogram mass. All right? That makes sense. So mass is a scalar quantity, so you don't have to worry about direction of mass. Okay? And mass is always measured in kilograms in physics. Okay? The symbol for mass will be a lowercase m. Do not get that confused with the unit of meters, okay? The unit for mass in MKS system, which is meters, kilograms, seconds, the unit for mass will be in kilograms. In CGS system, this is the one chemistry people use all the time, right? CGS is centimeters, grams, seconds. We're not using grams here because we're playing with much more massive objects. Physicists, we like to go big. All right? Chemistry people, they play with small stuff. In British system, mass is measured in slugs. I don't think this is like those slimy creatures that come out after rain that leaves slime behind, right? This slug is different kind of slug. So if you're interested, look it up. It's actually pretty interesting. This is a huge unit, by the way, slug. Okay. like average person would have mass of maybe 50 kilograms, but in slugs you may have maybe 4 slugs. Yeah, so it's a huge quantity. That's right. All right. Another term we need to know, right, is force. Force. A push or a pull is the thing that causes acceleration. All right? So, this force is a very abstract concept. Okay? In fact, we can never really talk about acceleration without stating the thing that causes acceleration. Okay? So acceleration due to gravity, right? Acceleration on the bat on a baseball due to a bat, and acceleration of a car due to friction will be some examples that we need to talk about. So when you exert a push or a pull on an object, you say you are exerting a force on the object. All right? Forces cannot be seen. Right? You cannot see forces. You cannot taste it. You cannot, right, touch it. They are known for by the effects they cause. You can only like sort of indicate the forces present when you see an object accelerate. Okay? So effect 1. Forces cause acceleration. Yeah. When you push on something, you will change its velocity. And when you change its velocity, you are causing acceleration. Okay? Effect 2. When you push on something, it pushes back at you. We're going to have to talk about that a little bit more in detail later. Okay? So, but what if a car is stuck in the mud and a giant rat-tailed, owl-faced, bloodshot-eyed monkey, right, pushes, right, which is exerting a force, and the car doesn't move. There's no acceleration. Is the monkey still exerting force on the car? And the answer is? Yes. Yeah, of course he is. It's pushing it. So it's definitely exerting a force on it. But why isn't it moving? Something's holding it back, basically, right? So the monkey, even though is applying the force in this direction, right? Something is pushing it back to counter the monkey's push, and that counter must be the same as the amount of force that monkey is applying. Okay? So we have to really think about the net force. The net force. And the net force is simply adding up all the forces, right? That is, this force, the purple force, right, plus the aquamarine force. Okay? So when I add them up, it looks like this force is in the opposite direction of my, right, right? So my net force, when I add them all up, the magnitude of that is simply 0. Okay? So this net force is what's really causing the acceleration. So if my net force goes to 0, I cannot have any acceleration. So net force is basically sum of all forces. Okay, net force is sum of all forces. We've seen this problem before in vectors, right? When we did vector problems. Okay? So we're going to have to use vectors again to solve some of these force vectors. Okay? So this is your homework. Okay? And Sir Isaac Newton wrote 3 laws of motion. All right? And they're like one of the fundamental, like, cornerstone of mechanical physics, all right, or Newtonian physics. And these 3 laws pretty much helps us understand the dynamics. The first law of motion is law of inertia. Okay, law of inertia. This law of inertia states that an object will continue in its state of rest or constant velocity. So there are 2 parts to this: rest or constant velocity, both magnitude and direction, unless the object is acted upon by some net force. Okay? So to like break that down, it means an object will continue to stay in motion in straight line, or if it's at rest, it wants to continue to stay at rest unless some net force acts upon that object. Okay? If it's at rest, it wants to stay at rest. If it's in motion, it wants to stay in motion in a straight line at that constant velocity. Okay? That's inertia. Okay? So the net force is defined by sum of all forces, right, acting on an object. The Greek letter sigma means the sum of, and therefore sigma F means the net force. We already know that, right? If the net force F sigma, or sigma F, is equals to 0, then acceleration must also equal to 0. All right? There's no negotiation on that. All right? When net force is 0, the acceleration must be 0. Okay? This is a huge change from Aristotle's belief, okay, that a body's natural state is at rest. So Aristotle believed object's natural state is always at rest, but that's not true. Newton came by and said body's natural state is whatever state it has at that moment. Okay? Now Galileo studied ball rolling down ramps. Okay? And he realized when he actually he had these beautiful ramps carved out of wood, and these columns were beautifully carved out, you know, by artists. And these ramps, he studied the motion of ball rolling down the ramp. And he noticed the speed of the ball gets faster and faster and faster as it comes down the ramp. I saw the actual original ramps at his house. It's pretty cool. It's really nice. All right. And then, what else did he notice? He also noticed that when he releases this ball on this ramp, as it comes down to the bottom, and then if he puts another ramp on the other side, right, the ball somehow knew exactly the height where it was released, and the ball went up to the other end almost exactly the same height. So the Galileo said, wow, how did this know? How did this ball know exactly the height that it started from? You know, does it have a memory? You know? So he decided to trick this ball and say, you know what? I'm going to put a different angle on this, and I'm going to make this ramp less steep and make it more shallow. So see if it doesn't travel only this same distance here and then stop, you know? But he recognized that the ball, again, went up to about the same height where it started. So he said, you know what, but what if there's no ramp on the other side? What would happen then? If there's no ramp, what's going to happen to the ball?
It's going to slow down until it stops.
But where?
The length of the hypotenuse, or the length of one of the legs on the right triangle is equal.
Nah. This ball would never stop. It would just go forever.
What about friction?
Oh. What if there is no friction?
Well, that's impossible.
It's possible.
In real life,
Well, Galileo determined that this ball would just go forever. So what I did was, back in the old days, I used to teach academic class as well as AP class. And when we got to this section, I have this long track, and then I have this huge ball, right? And I told them to stay, like stand, where this ball would stop when I release it from this end of the hallway out towards the bus circle. And then if the ball stops right where you are standing, you will get an A for the whole year, the rest of the year. Yes! And they would all stand, you know. Some would stand by the bathroom door, some would stand by the library first door, some will stand by, right? And some will stay like 2 doors down, you know, 3 doors down. And I released the ball. You know what happened? It rolled all the way down to the bus circle. It hit the door and rolled all the way back towards me. And I just picked it up and I walked away. If the door wasn't there, it would have just kept going. Yeah. Even though there was friction, it just kept going. And after it hit the door, it came back. Yeah. To me, like all the way back. So Galileo said, you know what? As long as there's no force acting on that ball, it'll just keep going forever. Which is completely different than what Aristotle said. Aristotle said the natural state of any object is at rest. But that is just half of it. When it's in motion, it will stay in motion. That's inertia. Okay? Yes, friction will slow it down eventually. Right? But that friction is so negligible if you have nice, smooth, polished floor, waxed floor here like the hallways. It will just go. It'll just keep going. You'd be surprised how far that thing will go. Yeah. All right? So it's very important to understand that yes, friction will slow it down, but if the friction is negligible, it won't. So if we were to take a look at this object, okay, this object, let's say it is at rest, okay, or it could be in motion. We don't know, okay. If I were to, label all the forces acting on this object, okay, this is what we will have. Here, we cannot escape gravity. the gravitational pull by the Earth on this object, we're going to call that Fg. Then, there's gravitational pull by this object on Earth. That is Fg prime. We also have F normal. F normal is what the surface is applying onto this object. The surface has to apply force onto this object so that it stays on the surface. We also have F normal prime, which is the surface of this object applying force onto the surface. And if we push this object with certain force, let's say, right? Let's say F push this way. And it's not accelerating, let's say, then there must be something holding it back. Right? There must be something holding it back, and that is the F friction. So when I add up all these forces, this force, this force, this, my net force becomes what? Now my net force becomes 0. Therefore, my acceleration is 0. Does that mean this has to be at absolute rest? Leo? Why not? Huh? Well,
because all atoms are always in motion.
What if this was already in motion?
Constant velocity means like acceleration is 0.
Correct. So just because your acceleration is 0, it doesn't mean it has to be at absolute rest. When acceleration is 0, it could be in motion in a constant velocity. It could be moving at a straight line with a constant speed, and you could still have acceleration of 0. Very good. All right? Yes, Henry?
What does Fg prime represent again?
It's the force of gravity by the object on Earth. We will learn about this more in detail in Newton's third law. Yeah. But for now, just understand, if I have all these, 6 forces, add them up, my net force will cancel out to 0. However, that doesn't mean it has to be at rest. It could be in motion with a constant velocity. Right? Just because my acceleration is 0 doesn't mean it has to be at rest. It could be also in motion with constant velocity. That was the whole point. Yes, Henry?
Does a ball reduce the friction of the object?
I'm sorry?
Does like a ball reduce the friction of the object? Like if you push this square or a cube down
We will learn about friction much more in detail, but for now, if the ball is rolling versus sliding, they're two different motions, and we'll talk about that much more in detail. I'm glad you're thinking it, but hold on to that thought. Yeah. Matter of fact, you need friction in order for a ball to roll. If you don't have friction, the ball would not roll. It would just slide. So we'll talk about that more in detail later on. Chapter 11, don't worry. That's when it gets really hard. This is easy stuff. All right. We're building up though, we're building up. Here's Newton's second law. Now, he had many laws, obviously, right? I mean, you'd be lucky if you have one law written by you with your name on it in physics textbook. Like, you'd be like a legend forever. He had so many laws, right? He just didn't have brother-in-law or any mother-in-laws or He was never married. Yeah, he didn't have any in-laws. Second law for Newton is F equals ma. So first law is law of inertia. The second law is F equals ma. All right, F equals ma. So what does that mean? It means he stated as the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. The direction of the acceleration vector will be in the direction of the net force vector. So first of all, the direction of acceleration and direction of net force will always be in the same direction. And acceleration will be directly proportional to the net force acting on the object and inversely proportional to its mass. This is the way he described it. Okay? And if I multiply mass to both sides, this becomes the Newton's second law. The net force is equal to ma, or F equals ma. All right? So the net force, or the sum of all forces, or sigma F, it simply means adding up all the forces, F1 plus F2 plus F3, right, plus dot, 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 dot. And we also said the net force is equal to ma. So we can set these two forces equal to each other, the net force is equal to each other, and we can now say ma is equal to simply F1 plus F2 plus F3 plus dot, dot, dot. This is very important. You must know how to set these two equal to each other and identify all these forces. If you cannot do this, Chapter 5 will be very difficult for you. All right? So what is the unit for force? Well, force is equal to mass times acceleration. F equals ma. Mass is measured in kilograms. Acceleration is measured in meters per second squared. So kilograms times meters per second squared should give you kilograms times meters per second squared. This is the unit for force. They decide to give this derived unit in honor of Sir Isaac Newton, and they called it 1 Newton. This is the unit for force. Okay? Okay? So here's an example of force equal to positive 10 newtons x head is applied to two different masses, right? We are applying same amount of force to two different masses, one mass being 10 kilograms, other mass being 2 kilograms. The acceleration for mass 1 and acceleration for mass 2 should be different, right? So if you were to calculate acceleration for mass 1, this net force of 10 newtons divided by 10 kilograms gives you 1 meter per second squared x hat. However, for acceleration for mass 2, the net force of 10 again divided by mass of 100 kilograms. So 10 newtons x hat divided by 100 kilograms is equal to 0.1 meters per second squared x hat. So acceleration is inversely proportional to the mass or the inertia of an object. Therefore, mass 2 must have 10 times more inertia, or the resistance to motion, than mass 1, because it has 10 times less acceleration. Right? That makes sense? Because they're inversely proportional. Alright? Alright. Now we already know how to do this because we did this before when we were doing chapter 3. So let's take a look. We have 10 kilogram object. Right? We have 10 kilogram object. This is bird's eye view, by the way. So we're looking straight down from cloud number 17 above, right? So we have 10 kilogram object in outer space, far away from any gravitational effect, is subject to two forces, F1 and F2, okay, as shown. So if F1 and F2 is like this, and it's being pulled simultaneously, F1 being pulled this way and F2 being pulled this way simultaneously, and it's going to behave as though only one force is pulling on this, and it will accelerate towards that force. So if I pull, what happens? Wow, wow. Did you see that? It accelerated that direction, right? So these two forces behaved as though only one force was acting in that direction to make that object accelerate in that direction. What force is that? Louder? Net force. So we should calculate the net force, huh? Well, once we calculate the net force, we can divide that net force by its mass to get the acceleration. We good? All right. So let's take a look. Find the acceleration. For part A, we need to find the net force. And the net force is simply, right, F1. I'm going to represent F1 with my aquamarine blue, plus F2. And F2, I'm going to represent that with my passionate purple. Yes. So F1, if I break this up into its components, my F1, this one is easy, right? It's simply 0 x hat plus 20 y hat newtons, right? So that one is easy. However, my F2, this looks like in the fourth quadrant, so my proper angle, theta, is really 330, right? So if you do, F2x is equal to F2 cosine theta, and therefore 30 times cosine of 330 gives me positive 26 newtons x hat for my F2x, right? And my F2y is equal to F2 times sine of theta, which is 30 times sine of 330. So my F2y is equal to simply negative 15 newtons y hat. So I can represent my F2 in Cartesian form as 26 x hat minus 15 y hat newtons. So let's add them up. So here's my F1. My F1 is equal to, all right, let's write it out. Thank you. 0 x hat plus 20 y hat newtons. And my F2 is equal to 26 x hat minus 15 y hat newtons. So if I add them up, I get my net force, and my net force comes out to 26 x hat plus 5 y hat newtons. That means this thing will have my net force going somewhere like this. Okay, this is my net force. Okay, and this is the angle theta for my net force. Okay, so what is the magnitude of this net force? The magnitude of my net force is equal to simply square root of, right, 26 squared plus 5 squared, and it's in first quadrant, so it's pretty easy for your theta. This comes out to 26.5 newtons as your magnitude of your net force. The theta, which is in first quadrant, is same as your beta, which is tan inverse of, right, opposite, which is F net y, right, so 5 over 26, and this comes out to 10.9 degrees. So your net force in polar form is equal to 26.5 newtons, comma, theta is equal to 10.9 degrees. To find acceleration will have exact same direction as my net force. So we already got the direction for acceleration. However, you can do this acceleration two ways. Your acceleration is equal to simply the net force divided by its mass, right? So in the Cartesian form, all you have to do is say, okay, it is 26 x hat plus 5 y hat newtons, divide that by 10 kilograms. Right? So if you divide both by 10 kilograms, your acceleration in Cartesian form will be simply 2.6 x hat plus 0.5 y hat meters per second squared. So that's Cartesian form for my acceleration. Or you could do another way, which is the magnitude of my acceleration is simply the magnitude of my net force divided by its mass, which is equal to 26.5 newtons divided by 10 kilograms, which comes out to 2.65 meters per second squared. That is the magnitude of my acceleration. But the directions should be exactly the same as my net force's direction. So you could also write down acceleration as 2.65 meters per second squared, comma, theta is equal to 10.9 degrees. Or you could square this, add them up, and then take a square root of it, and you'll get the exact same 2.65, right? Then tan inverse of 0.5 over 2.6 will get you exact same 10.9 degrees. There's so many correct ways to do it. All right? Then it asks, part B, if the object is at rest at t is equal to 0, how fast is it moving after 3 seconds? So for part B, right, if object is at rest, so we know VI is equal to 0. How fast is it moving after 3 seconds? We're looking for VF. when t is equal to 3 seconds. But we also know the acceleration is equal to 2.65 meters per second squared. This is easy. Use equation number 1. Oh my God. If you still don't know this, you are in trouble. Use equation 1. And equation 1 is Vf is equal to Vi plus At. So Vf is what we're looking for. Vi is 0 plus 2.65 times 3 seconds. So my Vf comes out to 7.95 meters per second. Right? So this is how fast it's moving. If they were asking for the magnitude and direction, what would the direction for this object be moving at this speed? Huh? 10.9 degrees, because it's in the same direction as my acceleration. Okay? So if they're asking for the velocity of this, it would be just 7.95 meters per second, comma, theta is equal to 10.9 degrees. What about part C? Part C asks, find the third force needed so the object is in static equilibrium. We did something like this already. So for part C, we know, here's the center of the object. We know my net force is going in this way, right? That's my net force. If the third force, F3, is in same direction, opposite direction with the same magnitude, right? This way, F3, it would cancel everything out. So my F3 is equal to, right, simply negative of the net force. So you can say my F3 is equal to negative of, right, 26x hat, right, plus 5y hat newtons. So you can say now my F3 is equal to negative 26x hat minus 5y hat newtons. Or you can say my F3 is equal to the magnitude of my net force, which is 26.5 newtons, comma, the angle should be 180 plus this theta. So my theta 3 should be 190, right, 0.9 degrees, and that also would work out fine for my F3. Are we good? Yes, Henry?
Could you also say, like, what's it called, the polar form, could you say negative 26.5?
No. Why not?
The magnitude cannot be negative?
Correct. Magnitude cannot be negative. So you cannot say negative 26.5. Should have known that from chapter 3. All right? Magnitude cannot be negative. Magnitude is always going to be positive. Any questions? So you got a lot of homework to do. All right? I'm going to continue on with Newton's third law. Let's get it out of the way. Okay? Newton's third law. Newton's third law is also famously known as action-reaction pair. You really have to know how to identify what's action and what's reaction. Okay? So let's read about this. When one object object, let's say A, exerts a force on a second object. I'm going to call that second object B. The second object will exert a force on the first object. The second force will be equal in magnitude but opposite in direction as the first force. So you really have to understand, right, the forces come in pairs. And using on and by terms, you can determine which one is action and which one's reaction. And picking which one's action is arbitrary. If you pick one to be action, then the other one has to be reaction. Okay? So if action is identified already, let's say by this, right? Let's say action force is the force exerted on the tray by the hand. So this is the action force. Then the reaction force is simply the force exerted on the hand by the tray. So here, the hand is supporting this tray, so force on tray by hand, and then the reaction is the tray is pushing down on the hand, which is the force exerted on the hand by the tray. This is action, reaction. So you could say this is action, and this is the reaction. Okay. Or you could flip it, you know. It doesn't really make a difference, really. All right? You could flip it. Yeah.
What if you were to like throw the tray forward? Would that, like, what would be the reaction in that case? Like,
That's a little bit more complicated because as soon as you let go of the tray, there's no more force acting on it except for gravity. So the action force would be Earth pulling on the tray. The reaction force would be the tray pulling on the Earth.
how does the tray pull on the Earth?
We'll talk about that. That's the next page. Yeah, yeah. So that's the next page. So we'll talk about that more in detail. So here, the action forces do not act on the same object. So that's the difference. Okay? It's one object acting on another object. It's not two forces acting on one object. So make sure you understand the difference. Okay? Like the one in the earlier problem when we saw the monkey, right, pushing the car. This is not action-reaction pair because monkey is pushing on the car and the friction is also pushing on the car. Okay? So these two forces are acting on one object. So that's different than two forces acting on each other. Got that? All right? There's a huge difference. We have to understand this word normal force. This normal force is going to be used a lot in this chapter and the next chapter as well. This normal force will be defined as a supporting force. By the surface. Right? That is perpendicular. That's what that normal means. It's mathematical normal. That doesn't mean it's not strange. Okay? That is perpendicular right? Which is mathematical normal, right, to the surface. All objects near the surface of the Earth will be affected by gravitational pull of the Earth, right? So this weight force is caused by Earth pulling on the object. That's weight. So this will be action force, let's say. The reaction force is the object is pulling on the Earth with the exact same amount of force. So this is action, and this is the reaction. This normal force, which is the surface of this table supporting the object, let's call that action. The reaction force is the surface of the object applying force onto the surface of the table, which is the normal prime. So make sure you understand the difference between the normal force and normal force prime and weight prime. Common misconception people have is the normal force and weight are the action-reaction pair, but they are not action-reaction pair. And we will talk about that more in detail later on. Okay? So make sure you don't get those two confused. Okay? So this, make sure you read this. This is definitely part of the AP multiple choice type of question. Yes?
Could you go into depth of W prime real quick? Like,
I will. Here we go. Action-reaction pairs continue. All right? According to Newton's third law, when an object falls to near the Earth, right, or the Earth near the surface of the Earth, there is force exerted by the object on Earth. So the reason why objects accelerate towards the Earth is because gravitational pull between the object and the Earth. Okay? Later on, we're going to learn about Newton's gravity. Well, as much as the Earth pulls onto this object, let's say an apple, right? Apple pretty much pull exactly the same amount of force to the Earth as well. And that's the action-reaction pair. It sounds incredulous, but as the Earth pulls on the apple pulls on the Earth with the exact same amount of force. Then you may ask, yeah, but then how come we don't see like Earth like going up towards the apple, accelerate towards the apple, right? Correct. Because the Earth is so massive, yes, it does accelerate towards the apple. But what is the actual value of that acceleration? You could probably calculate it, but there's no way you could probably measure it, because we don't have instrument that is so fine to measure that kind of acceleration. So here we go, right? We said the force of gravity on ball, let's say, by Earth must equal to the force of gravity on Earth by ball, right? They have to equal to each other. The mass of the ball times acceleration of the ball, right? So Fg is equal to simply m ball times acceleration of ball. That has to equal to mass of Earth times acceleration of Earth. Let's say the ball has mass of 0.5 kilograms. Okay? We can definitely measure the acceleration of the ball. And that acceleration of the ball is 9.8 meters per second squared. We could definitely measure that. Okay? That has to be same as mass of the Earth. Mass of the Earth is 6 times 10 to the 24th kilograms. That means we have 6 with 24 zeros following it. Okay? Times acceleration of the Earth. This is 4.9 newtons. That has to be same as this. So if we solve for the acceleration of the Earth, it is 4.9 divided by 6 times 10 to the 24th. That is billion times smaller than Microsoft 0. Okay? That is nearly 0. That's why we won't be able to see the Earth going straight up to the ball or the apple. Okay? I mean, if you actually plug this into your calculator, they'll laugh at you, right?
It says that it's 8.16 repeating times 10 to the negative 26.
Right? And Microsoft 0 is like 10 to the negative 16th. So that's like 8 zeros, which is like a billion times smaller. Yeah. Okay? So right? That's ridiculously small. What is the size of an atom?
Small.
10 to the negative 10th angstrom. That's 10 to the negative 15 times smaller than the size of an atom. I'm not saying 15 times. That's 10 to the negative 15, which is, you can't even make a ruler to measure this kind of acceleration. Yes, Henry.
So, does the object have to be falling? What if it's just like...
Oh, that's a good question. That's the next thing we have to talk about. Yeah. Right now, we have a very, very nice relationship between Earth and our moon. Our moon is so important. Without our moon, we wouldn't exist. Seriously. Our moon is protecting Earth so much you won't believe. Without our moon, we wouldn't even have our tide. We wouldn't have all these really cool effects. However,
I haven't even started this back
here,
here. Page is this?
we're on page 7, Doc. Earth. Earth attracts the moon. So this attractive force.
Say that again. What happens?
Will you hush? All right.
How many honors packets do you need these days? 80?
Yeah, 80 would be good. Thank you.
Yeah.
So this is
Not happy.
gravitational pull of on moon by Earth. Okay? Gravitational pull on moon by Earth. Well, that's the action force. Okay, this is the action force. The reaction force is same amount of force where Fg is being pulled by the moon. So Fg of on Earth by moon. Whoa, what was that sound? All right? That's the action-reaction pair. So, we need to know how to identify these things. Yes?
What if the moon just disappeared one day? What would happen to us? Or let's say like, like someone struck the moon and then stole it. What would happen to,
Here, you own a stubborn talking goat that refuses to pull a box, saying that when he pulls on the box, the Newton's third law states the box will pull on him with equal force in the opposite direction. Therefore, the forces would balance out and there will be no net force. He goes on to say that since there's no net force, Newton's first and second law states that there can be no acceleration. How would you reason with this stubborn goat to explain to him he can indeed pull the box? Now, first of all, you have to understand that this box here is on a frictionless surface. Like, let's say this has like billions and billions of buckyballs like underneath the box, which will make this box very, very frictionless. So even the slightest push either way would make this box accelerate. All right? So all right? Now, the goat's saying, listen, I went to Harvard and I learned about physics and I learned about Newton's three laws. And according to Newton's third law, if I pull on that box, that's action force, the reaction force will be pulling me back, so it's not going to accelerate. And if there's no acceleration, it's not going to move. So if it's not going to move, according to first law, it's staying at rest, so it will stay at rest. So why should I even pull this thing? Is the goat correct? No, obviously not. But why? Is the goat really pulling the box? Where is the goat applying the force? Who said that?
The ground.
The ground. The goat is applying the force to the ground. And the goat is pushing this way to the ground, and the ground is actually pushing back this way to make the goat accelerate that way. And the box just follows. Okay? So the goat is really not pulling on the box. The goat is actually pushing into the ground, and the ground is actually pushing the goat forward. All right? Now, think about it this way. I'm going to stop here.